All right, we are tasked to find y prime in each of the following implicit equations. All right, so the tactic for this is we want to differentiate both sides, and then somehow a y prime should show up through the chain rule, and then we want to isolate that y prime. So if I want to start with this first one, just rewriting it. My tactic is to differentiate both sides with respect to x, all right? So this first equation implies that 4x cubed, that's due to the power rule, plus, okay, so I have to do the chain rule in this case. The key here is to remember that y is a dependent variable of x, okay? So I have to differentiate the outside function first, which in this case is the sine, and then I have to multiply by the derivative of the inside function. Y is a function of x. Okay, so we have plus the cosine of y, that's the derivative of sine. Then I have to multiply this by y prime. Again, that is because of the chain rule. I have the sine of a function. Sometimes in my brain, really how I look at this, I look at that sine of y part as the sine of f of x, okay? Some function f of x. And if I were to take the derivative of this guy, I would then have to take the derivative of the outside function, sine, and then multiply by the derivative of the inside function, f prime of x. So that's really what just went down. And on the other side of this equation, it looks like I have the product of two functions, which means I will have to use the product rule. In other words, I have the derivative of the first function, x cubed, times the second, y squared, plus the first function, x cubed, times the derivative with respect to x of the second function, y squared. This part's not too bad. This is equal to 3x squared times y squared, plus x cubed, but the derivative of y squared, again, this is the composition of functions. I have the outside function is something being squared. So the derivative of something squared is 2 times that something via the power rule. But then, of course, I have to multiply by the derivative of the inside function, which is y prime. All right, so overall, let's bring this down so I can see the full equation. And then our goal simply is to solve for y prime. So what I'm going to do is subtract this from both sides of my equation and subtract this from both sides of my equation. This is basic algebra. Oops. All right, so again, what I just did was I subtracted this from both sides of my equation, and I also subtracted this from both sides of my equation. Why? Well, we want to get y prime by itself. We want to isolate y prime. We want to find some sort of function that will tell us the slope of this original curve right here at any xy value. Any point on the curve, I should say. All right. What do we do next? Well, what I'm going to do is I'm noticing that there's this green y prime attached to both of these characters. So what I can do is factor it out or sort of undistribute it. So that's going to look something like this. Left-hand side, nothing's going to change. But then on this side, I want to use parentheses, 2x cubed times y minus the cosine of y, all times y prime. And this is going to give me my final answer. Y prime, by dividing both sides by this character right here, y prime is the same thing as 4x cubed minus 3x squared times y squared, all divided by 2x cubed times y minus cosine of y. Okay, again, that's from dividing both sides by this character right here. Here we go. I think the only task for this first question is to isolate y prime, or to solve for y prime, so we just did it. Notice that this is a function, this is a machine that will tell me the slope of the original curve at any point on the curve. That's the most powerful thing about this implicit differentiation. We can now solve for slopes for implicit curves rather than explicit curves. All right, let's try the next one. We got an exponential function, which we all know and love. All right, process looks the same, you guys. We're just going to take the derivative with respect to x on both sides. All right, taking the derivative here, the derivative of the outside function is this e to the something. So the derivative of e to the something is e to that thing. So I'm going to start like this, e to the 2x. But then I have to multiply by the derivative of the inside function, which is 2x. Over here on this side, we have the derivative of the outside function, which is cosine. So the derivative of cosine, that's also known as negative sine. And I have to evaluate that at the inside function. And then after doing so, I then multiply by the derivative of the inside function with respect to x. That's really important. So again, that's just the chain rule. And now, the derivative of 2x is 2. And I have negative sine of x plus 3y here. Then I have to multiply by the derivative of this function right here, or this sum of functions, really. But the derivative of a sum is the sum of derivatives. So the derivative of x with respect to x is 1. And then I have plus 3. And then what I really have is the derivative of y with respect to x. But hey, that's also known as y prime. All right, my goal is to isolate y prime. Here's what I would do. I would say, what is the best way to do this? I would distribute this sine of x plus 3y. Probably the best way. I mean, we're going to have complex fractions either way. Or we can just divide both sides. I'm going to do it like this. Because then we would have to find common denominators at the end anyways. Minus sine of x plus 3y. Minus 3 sine of x plus 3y times y prime. So again, all I just did was I distributed this character to both the 1 and this character. Adding this to both sides of the equation, that'll get me here 2 e to the 2x plus sine of x plus 3y is equal to negative 3 sine of x plus 3y times y prime. That will tell me that y prime is the same thing as negative 2 e to the 2x plus sine of x plus 3y, all divided by 3 sine of x plus 3y. Awesome. All right, so that's the general process for solving for a y prime. Takes a little bit of practice, but we can make this a little bit more complicated by what if we also had to solve for y double prime. So in each of these cases, we don't just have to find y prime, we also have to find y double prime. And we need to solve for y double prime in terms of x and y. So we can't leave a y prime in our result for y double prime. And I'll explain what I mean once I solve some of these. 2x cubed minus 3y squared is equal to 8. Taking derivatives on both sides with respect to x, that will bring me here 6x squared minus 6y times y prime. This is really crucial. All right. So again, when I take the derivative of this with respect to x, that's the expected derivative. When I take the derivative of this with respect to x, since y is a function of x, I have to multiply by the derivative of y because of the chain rule. And on the other side, I have equals 0, indeed, because the derivative of 8 with respect to x is equal to 0. All right, I see a 6 cancels everywhere, and it looks like y prime is going to be the same thing. Nice, easy derivative here. After solving for y prime, I get x squared over y. Let me make sure I did that right. Yep, all right, that looks good. So I solved for y prime. Now the goal is to find y double prime. Okay, so in order to do that, I have to take the derivative on both sides of this with respect to x. Okay, that's going to bulk things, or that's going to make things kind of gross to look at. So I'm just going to kind of recall y prime is equal to x squared over y. All right, so the derivative of y prime is y double prime. So this left-hand side, I'm just going to write y double prime, and that's actually what we're solving for. But then, to take the derivative on the other side, what I have is a quotient. So I have to do the quotient rule. So this is equal to the bottom function times the derivative of the top with respect to x minus the top function times the derivative of the bottom with respect to x, all divided by the bottom function squared. That's just the quotient rule. And then you just take these derivatives one by one. So we got y times the derivative of x squared with respect to x, that's 2x, minus x squared times the derivative of y with respect to x. But you guys, no joke, I mean this with everything, that is y prime. Those are the same object. They are synonymous. So what I have is y prime right there, all divided by y squared. All right, let's see what's going on. Notice that I need this y double prime purely in terms of y's and x's, and I have this green y prime sitting here. So what I'm going to do is grab this version of y prime and plug it into this one. So this is going to equal 2xy minus x squared times x squared over y, all divided by y squared. And my immediate thought here is I have fractions inside of fractions, so to clear those, I'm going to multiply the top and the bottom by y. That will bring me here. This is the same thing as 2xy squared minus x to the fourth, all divided by y to the third power. And that is my formula for y double prime. Okay, we solved for both of them. These can get chaotic, though. So let's try a little bit more of a challenge here. I think this other example, I made it a lot harder. Yeah, okay, so we got x times y is equal to sine of x plus y. Let's see how that looks. Here's part B. All right, on the left-hand side, I have to abide by the product rule. And that's going to be the derivative of the first one times the second, plus the first one times the derivative of the second one. On the left-hand side, I have to abide by the chain rule, which means the derivative of the outside function, which is the cosine evaluated at the inside function. So don't change the inside function, but then you do have to multiply by the derivative of that inside function. All right, let's decode each of these. What I have right here, the derivative of x with respect to x is 1. So all I have left is y right there. Then I have plus x times the derivative of y with respect to x. Oh, but that's y prime. Those are the same thing. Over here on this side, I got the cosine of x plus y, and then I have times the derivative of this sum right here. But that's going to be the derivative of x plus the derivative of y with respect to x. That's going to look like 1 plus y prime. Okay, I have to solve for y prime here. It looks like this implies that y minus the cosine of x plus y is equal to the cosine of x plus y times y prime minus x times y prime. Solving for y prime, it looks like I have that y, well, I'll write it like this. I'll show it'll work. Y minus the cosine of x plus y is equal to the cosine of x plus y minus x times y prime. And therefore, y prime can be written as y minus the cosine of x plus y divided by the cosine of x plus y minus x. Oh man, that's kind of an adorable derivative. I like how that one looks. But unfortunately, we are not done yet. We indeed have to also solve for y double prime. So this implies y double prime is equal to, so I have the bottom, this is going to be a mess, guys, times the derivative of the top minus the top times the derivative of the bottom. Wow. It's okay. We're in the thick of it here. Okay, that is the quotient rule that I just used. Now let's take each of these derivatives. What we have, this is the same thing as the cosine of x plus y minus x times the derivative of y minus the cosine of, okay, so there's a lot going on here. So we have, first of all, the derivative of y with respect to x, that is also known as y prime. And then we have minus the derivative of the outside function here. Again, I'm zoned in right here. The derivative of the cosine is the negative sign, but it's already negative. So I actually think I'm going to get the sine. So positive sine of x plus y. But then I have to multiply this by the derivative of this inside function. The inside function is x plus y. And taking the derivative there, what we have is 1 plus y prime. Close parentheses here, minus this guy doesn't change. We have y minus the cosine of x plus y times the derivative of the cosine, which is negative sine. So I got negative sine of x plus y times the same derivative, 1 plus y prime minus 1. Is that what I'm looking at? Yep, minus 1. So again, I just took the derivative of this part right here. That's this right here. Fact check with me. And okay, so here's what I got. I still have to divide by that denominator. So we got the cosine of x plus y minus x all squared. All right, so what's going on here? How can I simplify this? Okay, I'm seeing a few things that we can do. One of them being we can factor these guys. Would that be helpful, though? Another thing I'm noticing, oh, check this out. This is kind of slick. Each of these, oh, okay, so this will make things a lot easier. Notice this. I have sine of x plus y here, and I have sine of x plus y right here. But I think we have another name for the sine of x plus y, and that's x times y. Oh, wow. Okay, so there is definitely something that can change. How about this? I will do 2 substitutions in one go. I will do switching y prime with its other identity right here, but simultaneously, every time I see a sine of x plus y, I'm going to replace it with x times y, because those are the same object. It's the same curve. Okay, so this is going to get swapped. These y primes are going to get swapped. Still going to be a mess, but we're on our way, you guys. This is the same thing as the cosine of x plus y minus x times, okay, this is where I have a big parentheses, y minus the cosine of x plus y, all divided by the cosine of x plus y minus x. Very computationally heavy here. Plus, here's where I'm at. So I just replaced this. Now I have the sine of x plus y, but I just fact checked, and that is x times y times 1 plus y prime. You know what? In hindsight, there might have been a way for me to clean up first. I wonder if that's true. I don't know. Plus y minus cosine of x plus y, all divided by cosine of x plus y minus x, closing parentheses here, making sure I have everything attached. One more parentheses. Also, here's something I'm going to observe. This is negative, so I can grab this negative, pass it through this set of parentheses, making this positive and this positive. So what I have is plus, in parentheses, y minus the cosine. So again, I'm right here. Y minus the cosine of x plus y, close parentheses. This negative got annihilated by this negative, and so did this negative. And also remember that sine of x plus y is the same thing as x times y. So right here, what I have is xy times 1 plus y prime, but this is y prime. So here we go, and we're almost done. Minus x, and then I have plus 1. Oh, close parentheses here, and then plus 1. All right, and making sure parentheses are all still good to go. Wait. Yeah, 3. One more right there. Okay. All divided by cosine of x plus y minus x to the second power. Okay, let's see. For sure, my next move is to clear these denominators. Best way to do that. Okay, so I'm going to multiply the top and bottom by that denominator. I just have to be careful with parentheses. I'm nervous I've made just things difficult for myself. No, I think we can do this. So parentheses there, x times y. Well, let's do it. Maybe I should use colors. I think I will use colors to make this extra clear. Yeah, here, let me do that again. We'll use dark blue. Okay, in the denominator, it's just going to be this cosine of x minus y, or excuse me, cosine of x plus y minus x cubed, because I have another one of them right here. Again, I'm trying to clear these denominators. But how is that going to look here? I have two big parentheses here. This is like an A. Okay, so I have this times this thing. I'm going to want to distribute this blue thing into this part of that parentheses, because that's where I want to clear all these denominators. And then I also have this over addition right here. I have this times this thing. So this blue thing wants to distribute to this parentheses. So maybe in yellow, I'll point out the parentheses that I want to distribute the dark blue object through. And again, what I'm really doing is I'm distributing this thing through the entire denominator. So that means it's going to attach to these yellow parentheses and attach to these yellow parentheses. So let's see how that goes. I have the cosine of x plus y minus x times, I'll show it like this, Okay, so here's what I just did. I grabbed this cosine of x plus y. I'm only have worked with this set of parentheses here. This got distributed to this term right here. And this got distributed to this set of inside parentheses here, which means that it has to hit this term and the 1 right here. So here's it hitting the 1, and here is it hitting this fraction right here. And hopefully you're noticing why this was all useful. So I really just want to rewrite this plus y minus the cosine of x plus y. Okay, and then I have x times y. And then here's the blue part. The cosine of x plus y minus x plus, yep, another one of those, in parentheses, the cosine of x plus y minus x times in hindsight, I think I actually should have done a lot more algebra. Okay, lesson learned. Oh, hold on. How careful do I have to be here? Okay, so I really have 3 things that this thing distributes through. Yep. Because I'm missing this 1, so I have to do plus. Is that right? Yeah, so I have one more. Close that parentheses, and then, yeah. Okay, final stretch. I hope. So let's see. This parentheses here is attached to this parentheses here. This parentheses here is attached to this parentheses here. Pretty sure I got it all checked out. And then, whew, look at that, you guys. Then I have to divide by the cosine of x plus y minus x cubed. Oops. What a beast. All right. Oh, shoot. These guys cancel. That was the entire point. Oh, shoot. These guys cancel. That was also the entire point. Oh, man. These guys are gone. And I think that's it. So, what do we got going on? Ooh, and there's going to be some more cancellations that I'm noticing right here. So those guys are going to cancel. That's super nice. All that's left in that parentheses is a y. And maybe something else. I don't know. We'll just have to be careful here. All right. Rewriting. This is the same thing. It's the cosine of x plus y. Wait a second. Is that actually... Oh, you guys. I don't know why that is actually frustrating. Because then I could have just distributed this. Oh, that's super frustrating. What the heck? Oh, well. Because this would have canceled just immediately. This was just sitting there. Man, I had blinders on. That is really embarrassing. Am I in trouble by doing that? No. No. I think I'm okay. I mean, I haven't broken any laws. Okay, sweet. Because this one needed one. Yeah, this other side needed one. Okay. And then in parentheses here. Okay, so I got this y minus cosine of x plus y plus x times y times, looking at this part right here, x times y times this. So that's going to be cosine of x plus y minus x plus y minus cosine of x plus y. Oh, that's nice. Okay. And then I have plus y minus the cosine of x plus y times... All right, this is the part where I keep confusing myself. We got the cosine, x times y, times the cosine of x plus y minus x plus y minus the cosine of x plus y. And that is all in that thing. These guys cancel. That's really nice. But then I have this plus the cosine of x plus y minus x, close parentheses. That close parentheses closes this one, right? Yeah. Okay. Where'd it go? Okay. All divided by cosine of x plus 3, x plus y, minus x cubed. All right, so what's left over here? We have the cosine x plus y minus x times y minus the cosine of x plus y plus xy times y minus x, and that's it. And then we have plus y minus the cosine of x plus y. And here we got x times y minus x plus the cosine of x plus y minus x. Okay, it's sort of cleaning up, I guess. All divided by cosine of x plus y minus x cubed. Okay, let's see. What other cleaning up can we do? If anything. We have cosine of x plus y, so we have cosine of x plus y squared. I mean, is there anything more we can do? Is there any other cancellations that will occur? Maybe I'll do this for starters. This is the same thing as the cosine of x plus y minus x. Then bunching up all y terms. So it's going to be y times 1 plus x times y minus x minus the cosine of x plus y plus okay, same thing here. We have y minus the cosine of x plus y. And then we have x times y. How did I do it over here? Yeah, y times y minus x minus 1 plus the cosine of x plus y. Interesting. I feel like something's going to happen. Now the question is, should I send it and FOIL both of these? Something might happen. So this side's going to produce a minus cosine squared. This one will also produce a minus cosine squared. So we're going to have two of those. XY. This one's going to have... Ooh. No, I don't think there's anything nice that's going to happen. I'm trying to see the future here. This is probably it. I don't know. Maybe I should just leave this as homework. Look at all that work we just did. This is hilarious. It keeps getting bigger. It's starts like this. It just goes, it just devolves. There's our y double prime. Leave it in the comments if you found a better way to express y double prime. Oh, geez. I almost don't want to give up. It's going to be positive x cosine. Nope, that's not happening. Yeah, I don't think there's going to be a nice cleaning up. Anyways, yeah, those could get really intense, the y double prime types of questions, but that's okay. So let's see. Find the tangent line and normal line to the curve at the given point. Let's see. Okay, so this is not too bad. We just have to take the first derivative because that green y prime that we always pick up, that represents our slope. And if we want a tangent line and a normal line, all we need is a point, which we are given, and a slope, which we can find using implicit differentiation. So let's start with this first one. Taking derivatives, that's going to be the derivative of the first times the second. So that's going to be 1 times the sine of 2y plus the first times the derivative of the second. But that's going to be the cosine of 2y times 2 times y prime. And that y prime is our slope. And then I have... this is equal to the derivative of the first, which is y prime, times the second, cosine of 2x. And then I do plus the first times the derivative of the second, which is going to be minus sine of 2x. But then I have to multiply that by the derivative of 2x. That's 2. All right. And gathering all y terms to one side, or y prime terms to one side, and all non-y prime terms to the other, looks like I will have a sine of 2y plus 2y sine of 2x, and that's equal to y prime times the cosine of 2x minus 2x cosine of 2y times y prime. Okay, that tells me that y prime is the same thing. Through undistributing, factoring out, and division, it looks like we got sine of 2y plus 2y sine of 2x, all divided by the cosine of 2x minus 2x cosine of 2y. All right, nice. So that's our derivative at any point, but we are concerned about a particular point. Therefore, what we want to do is plug in the point pi fourths, pi halves. So every x value, I'm going to plug in pi fourths. Every y value, I'm going to plug in pi halves. Okay, so y prime, I'll go slope of the tangent line this time. Is equal to the sine of 2 times pi halves plus 2 times pi halves times the sine of 2 times pi fourths, all divided by, looks like the cosine of 2 times pi fourths minus 2 times pi fourths times the cosine of 2 times pi halves. All right, let's see if we know our trigonometry. We got the sine of pi, that's 0. We got the sine of pi halves, that's 1 right here. And then we have 0 plus pi, so my numerator is going to be pi. And then we have the cosine of pi halves, that's 0. And then we have minus pi halves times the cosine of pi, that's negative 1. Okay, so the ones cancel, or excuse me, the negatives cancel, and I have pi divided by pi halves. How many times does pi halves fit into pi? Oh, that's 2. Okay, nice. Slope of the tangent line is 2, which tells me that the slope of the, I'll use yellow, slope of the normal line is equal to -1/2. And then I use my nice formula, y minus y naught is equal to the slope of the tangent line times x minus x naught. And we have y minus the point that we know is on our line, that's pi halves, is equal to 2 times x minus pi fourths. Distributing, y minus pi halves is equal to 2x minus pi halves, multiplying by 2. It looks like we got 2y minus pi is equal to 4x minus pi. And I don't know why I'm throwing so horribly. You can just cancel the pi halves. Y is equal to 2x. Wow. Okay, for the normal line, we have y minus pi halves is equal to -1/2 times x minus pi fourths. Multiplying both sides by 8, if you will, we got 8y minus 4 pi is equal to -4x plus pi. Okay, so 8y plus 4x is equal to 5 pi. I like that one. Normal line, tangent line. Crazy. Okay, let's try another one. So I'm sort of running out of rooms, but we got y squared minus 2x minus 4y minus 1 is equal to 0. Now let me take it up here. Y squared minus 2x minus 4y. And what was the point? -2 comma 1. Taking derivatives, 2y times y prime minus 2 minus 4 times y prime is equal to 0. So we got 2 solving for y prime. I can divide everything by 2. So that'll be y times y prime minus 2 y prime is equal to 1. That tells me that y prime is equal to 1 over y minus 2. Okay, that means the slope of my tangent line, all I have to do is plug this point in. Apparently my slope only depends on y. So I grab this 1, since that's the y value, plug it in for y right here. So what I have is 1 minus 2, that's -1. The slope of my tangent line is -1, which means that the slope of my normal line is +1, and these are easy. So what we got is, for the tan line, y minus 1 is equal to -1 times x plus 2. Y minus 1 is equal to -x minus 2. So x plus y is equal to -1. Tangent line, done. For normal line, we got y minus 1 is equal to x plus 2. And that's easy enough. Y minus x is equal to 3. Normal line. So we got tan line and normal line. And that's it. Call it a day. All right, so we got both of these done. Last type of question. All right, we got the famous folium of Descartes. We want to find the slope of the folium of Descartes. So it looks kind of like this. This is what the folium looks like. We talked about it in the theory video. We want to find the slope of the folium of Descartes at 4, 2 and 2, 4. All right, let's check this out. All we got to do is take the derivative of this implicit differentiation, solve for y prime. Let's talk about it. So going over here, looks like I have a x cubed plus y cubed is equal to 9xy. Taking the derivative, that'll be 3x squared plus 3y squared times y prime. And that's equal to 9 times. I have to take the derivative of the product of x and y. That's going to be the first, or the derivative of the first, which is x, 1, times the second, which is y, plus the first times the derivative of the second, which is y prime. In solving for y prime, it looks like I got 3x squared plus 3y squared times y prime is equal to 9y plus 9x times y prime. That tells me that y prime is the same thing, after a little bit of algebra, y prime is the same thing as 3x squared minus 9y, all divided by 9x minus 3y squared. And that's it. And I want to evaluate this at 2, 4 and 4, 2. So my slope at 4, 2 I can write, a way to write that would be like this. You go y prime, and then there's this vertical bar notation at 4, 2. And that would equal 3 times something squared minus 9 times something, all divided by 9 times something minus 3 times something squared. Every time I see an x, I'm going to write a 4. Every time I see a y, I'm going to write a 2. Almost something nice happens, but I do see a 2 cancel, so that's going to be, and maybe I shouldn't do it like that. That's probably the worst way to do this. I'm going to do it anyways. Uh, 12 in the denominator, and we got 15 twelfths. 3's cancel, so we got 5 fourths. Nice. All right, let's try evaluating that at 2, 4. That is going to equal 3 times 2 squared minus 9 times 4, all divided by 9 times 2 minus 3 times 4 squared. All right, so that's the same thing. 4 comes out of the numerator. We got 3 minus 9, all divided by 2 comes out of the denominator, and we got 9 minus 3 times 8. This is the same thing as 2 times negative 6, all divided by 3 times 3 minus 8. That's the same thing as negative 12 divided by 3 times negative 5. That's the same thing as 4 fifths. Interesting. There's the reciprocal of this guy right here. I wonder what we're hinting at here. Very interesting. Okay, at what point other than the origin does the folium have a horizontal tangent? Okay, when I see horizontal tangent, I see that y prime is equal to 0. In other words, the slope is 0. So all we got to do here is grab our equation for the slope, y prime, and set it equal to 0, solve for x and y. So y prime equals 0. So here's for part B. Y prime equals 0. That implies that 3x squared minus 9y divided by 9x minus 3y squared equals 0. Multiplying both sides by this denominator and hoping for the best that x and y behave, this implies that 3x squared minus 9y is equal to 0, and that implies that x squared minus 3y is equal to 0, which means that x squared is equal to 3y. Oh, but shoot, that's one equation and two unknowns. So you might think, well, are we out of luck? And the answer is no, because we know that in our original equation, this equation also has to be satisfied. So don't ever forget the original equation. We know that the point has to satisfy this equation and this equation down here. So how do we move on from here? I would say that replace y with x squared over 3 in this equation. Each y is replaced with x squared over 3, so we got x cubed plus x squared over 3 cubed is the same thing as 9 times x squared over 3. And then solving, so we got x cubed plus x to the 6th power, remember your exponent rules, divided by 27 is equal to 3x cubed. Assuming x is not 0, in other words, we know that this has a horizontal tangent line at x equals 0 and y equals 0. At the origin it does. So we can multiply everything by 27 over x cubed, giving us 1 plus 27. No, sorry. 27 plus x cubed is equal to 81. That tells me that x cubed is equal to 81 minus 27. That's too hard. 54. X cubed is equal to 54. Am I right on that? I think I'm right. Okay, so 54 is what? 6 times 9. This is the same thing as 2 times 27, which means that x is equal to 3 root 2. Nice. And we know x is equal to 3 root 2, but y, or 3 times y, is equal to x squared. Which means that 3 times y is equal to 3 root 2 squared, and y is equal to 6. Okay, I did a few steps. So the point where it has a horizontal tangent line is 3 comma root 2. What? 3 root 2 comma 6. FOD has horizontal tan line at perfect. Yep, that looks good. Okay, last question. Find the coordinates of the point A on the folium where the tan line is vertical. Okay, so in my brain, that says that y prime does not exist. In other words, the denominator of our y prime is equal to 0. So we have 9x minus 3y squared is equal to 0, which tells us that 3x is equal to y squared. This is when the tangent line is vertical, which says the same thing as the slope doesn't exist, and we do the same process. Every time I see an x, I'm going to replace it with y squared over 3. And we won't have to do all the work again. Because look, this is the same equation that we had in the other one. Where did it go? Right over here. Except just this time, I'm solving for y. In other words, I immediately know that y is going to be the same thing as cubed root, or 3 root 2. I don't know if you guys caught that. Notice this equation. I have y's everywhere. That's the same equation that I have right here. Except instead of y's, it's x's. But what that means is, in this equation, when I solve for y, it's going to be the same result as when I solve for x in this equation. It's just a change of variables. And in fact, even worse than that, I think this other equation, yeah, this is also symmetric. This other equation was symmetric. So that means when I plug y into this guy, it's going to be the same result. So it's going to be, I know the full lemma of Descartes has a horizontal tangent line at 3 root 2 comma 6 and a vertical tan line at 6 comma 3 root 2. And that's it for that question.